Welcome to the first official lecture of COS 212, where we are going to start with the material of the prescribed textbook. Today we're going to discuss chapter 2, which deals with complexity analysis. This is an extremely important topic that we are going to refer back to throughout the semester, so make sure that the material covered in this lecture makes sense to you. This will be examinable, and like I have said, the material covered today will be referred to throughout the semester in the context of various data structures and algorithms. All right, so in this subject, we are going to talk about algorithms and data structures. And obviously, both the algorithms and data structures are our means of solving certain problems that we encounter. I think an algorithm is easier to speak about in this context. An algorithm is a sequence of steps that is intended to obviously achieve a particular goal, solve a particular problem. Well, it turns out that a single problem can be solved in a variety of different ways, but not every single solution will actually have the same efficiency. So what exactly do we mean when we refer to an efficiency of an algorithm? Some algorithms might require more space than others. Maybe they will use more variables. Maybe they will use 2 arrays instead of 1, etc., etc. Alternatively, some algorithms might actually take more time than other algorithms. And if I asked you which one of the two was more crucial, if you were asked to optimize the efficiency of the algorithm, what do you think would the programmers typically refer to? Space efficiency, how much memory you use, or time efficiency? In other words, how fast does it run? Well, technically, if you write an algorithm that requires more space, that maybe uses more variables or larger data structures, technically, if data is your only problem, storage space is your only problem, you can always buy extra storage, right? You can always buy more memory, you can always expand your supercluster or wherever you're running your algorithm. Typically, if you need more space, you can buy more space. Does the same apply to time? Well, it turns out that buying time is a lot harder. You cannot just buy a faster computer if your algorithm is really, really slow, because there is a limit, a physical limit to how fast the computers can actually execute commands. So if your proposed solution takes an unacceptable number of steps to actually get to the final goal, then perhaps you should try and find a different solution. So the bottom line is, between space efficiency and time efficiency, we mostly care for the time efficiency, just because it is a lot harder to work around in case you propose a solution that has very poor time efficiency. We are going to learn how to measure time efficiency of an algorithm, but before we step into the details, what you need to realize at this point in time is the way we're going to measure time efficiency. How fast does your algorithm run, given some data set you have to process? We will not talk about exact objective speed. So we will not speak about milliseconds or per byte or something like that. Rather, we are going to speak in logical units. So we will try to figure out what is the relationship between the total number of data items n and the time spent t that your algorithm will take. So in other words, we want to find out a mathematical relationship between how much data I have to process and how much time will I need for that, without referring specifically to bits, bytes, milliseconds, microseconds, or anything like that. We will basically speak of just generic data units and time units, and we will try to relate the two to each other. And of course, if you have done any maths at any point in your life, you would know that a relationship between the two variables is described by a function, right? So the function f essentially is going to be the expression of the efficiency of an algorithm. Given n data items, how many time items, how many time units will I require to actually process so much data? So the question for today is, how do you determine this relationship given an algorithm? Let's say I give you the pseudocode or actual piece of code and ask you to analyze it. Will you be able to tell me how do you actually figure this out? How do you figure out what is this relationship? What is this function that connects the number of data items to the number of time units required to process these items? Cool. So we have figured out that the relationship between how much data you're going to process and how much time it will take can be expressed as a mathematical function f. We are going to discuss how to derive this f for any given piece of code, but before we get there, let's just try and think a little bit about how to interpret these functions, right? Suppose I already have a couple of algorithms, A and B, for which I already know what the function is. So for algorithm A, my f of n is equal to 2n. How do I interpret this? What exactly does it mean? Well, this essentially tells me that for any n number of items that I'm going to process in my algorithm, number of steps, whatever, I will require twice as many time units. This kind of a relationship function-wise is linear. Hopefully you all have seen a linear function before. A linear function is basically just a straight line where obviously this coefficient kind of determines the slope of my line. So what exactly does it mean? On the x-axis, we are looking at the n, number of items, number of elements in your array, for example. And on the y-axis, we are looking at the time units required to process your array that can obviously grow in size. So what I'm essentially saying with this function 2 of n is if my array has 10 elements, then I will need 20 time units to process this array. The time unit can be a millisecond, microsecond. This depends on how fast your computer can go, but the general relationship is 10 to 20, right? Similarly, because the function is linear, if I have an array of size 100, then to process the entire array, I will need to use 200 time units. You can think of it as milliseconds for now, just to make it a little bit more concrete. But remember, we want to keep it abstract just so that it applies to any computer architecture. And finally, this is how the list is going to go. If I have 1000 data items, again, multiplied by 2, and that will tell you how many time units your algorithm will require. So this is what a linear relationship between data and time looks like. What else can you potentially encounter? What other kind of complexities can there be? Well, let's assume there is another algorithm designed to solve the very same problem. And for that algorithm, the relationship between data and time is actually expressed as a quadratic function, n squared. Again, if you have done any maths in school, you should know what this function looks like. This is essentially a good old parabola. This is how it looks. So once again, on the x-axis is my data, the size of my array, and on the y-axis is the number of time units I will require to process this array. This kind of a relationship is quadratic. So let's once again substitute some values and see how the number of time units will grow as the size of the array grows. So for 10 data units, data items, array elements, I'm going to square it. 10 squared is going to give me 100. So for an array of size 10, I need 100 time steps. For an array of size 100, again, calculate the square of 100, you will get 10,000. So for an array of size 100, I will need 10,000 time units to actually process it. Finally, if I go to an even larger array of the size 1000, how do I know how much time it's going to take me to process it? You square it, and 1000 squared is going to give you 1 million. So for an array of size 1000 elements, I will need 1 million time units to process it completely using this other algorithm. So, question of the day is, which of the two algorithms, if they were designed with the same purpose to solve the very same task, which one do you think is more efficient? In other words, which one do you think will run faster, in the long run? clearly it's the first one, right? Because look, I have 10, 100, and 1000 data units, 10, 100, and 1000, and the first algorithm for 10 only runs over 20 time units, while the second one would run for 100 time units, which is obviously larger. And as my array grows, the disparity between the two becomes more and more evident. The larger the size of the array, the more incomparable the two become. Look, the linear function only grew so much, while my quadratic function from thousands went to millions. So clearly the quadratic function is a lot less efficient. Like, this function clearly has a much steeper relationship between data and time. So here I will very quickly end up with a very, very slow solution, right? So quadratic is clearly less efficient than linear. Let's take it one step further. Let's say somebody stepped up and proposed a third solution, the efficiency of which was expressed with the following function to n plus n squared. Is this function quadratic or linear? If we were in class, I would pause and ask you, but again, if you did maths, if you have done some algebra, you would know that in a case like this, the second term would contribute more, right? So this function is actually still quadratic. You're still looking at a parabola. Like I've said, out of the two, the linear term and the quadratic term, it's the quadratic term that's actually going to determine the magnitude of the function at the end of the day. So let's again substitute values to see how this plays out. For 10 data units, you will have 120 time units spent. For 100 data units, you will have 10,200 time units spent, and for 1,000 data units, you will have 1,002,000 time units spent. So this current solution, algorithm C, is definitely more comparable to algorithm B than to algorithm A. So n squared dominates to n, clearly. This 1 million is more significant than the 2,000 that I slap on top of it. If I ask you now which one was more efficient, algorithm A or algorithm C, you should clearly very easily tell me that A is more efficient. Linear function doesn't grow as fast, so we would prefer A between A and C. What if I ask you to pick between B and C? Well, technically speaking, for 1,000 data units, B would only use 1 million time units, while C would use 1,002,000 time units. So C is slightly worse than B. But because n squared actually dominates both of them, in computer science, we like to simplify things a little bit, and we will say that if the two algorithms are both quadratic, then they're basically kind of equally bad. Yes, B is slightly better, but still, because both are dominated by this quadratic term, they are both quadratic. Therefore, compared to A, both B and C are just quadratic versus linear. Both of them are, just as bad, essentially. In general, in computer science, when evaluating the efficiency of an algorithm, we're not really interested in the exact function that perfectly describes the relationship between data and time. Instead, we usually are more interested in asymptotic complexity. In other words, an estimate, some kind of an upper bound for how bad it can be. And this upper bound allows us to easily compare algorithms to one another. So it is a simplification. You can obviously calculate the exact relationship between data and time, but quite often after figuring out this exact relationship, we will go ahead, figure out which term contributes the most, and use that most contributing term to describe the efficiency, the upper bound efficiency of any given algorithm or piece of code. Great, so in future when you see formulas like this, remember all you need to do is figure out which term is the heaviest one, and the other terms will not really matter so much in terms of asymptotic complexity of your algorithms. Okay, so we come to the definition of asymptotic complexity, which is expressed via the big O notation. Big O sounds a bit funny, but it's because this capital O is used as a mathematical expression of complexity of an algorithm. It's quite interesting that the big O notation, the asymptotic complexity notation, was actually proposed back in the 19th century before computers were even a thing by a certain German mathematician. So this is a strictly mathematical way of looking at things. And the idea of big O notation is that we say that a function f of n is asymptotically bound by some function g of n if there exists a certain number c such that c multiplied by g of n would be greater or equal to f of n for all n greater or equal to some capital N. And again, this might sound like a mouthful, but the idea here is actually quite simple. If I say that f of n is bound by g of n, if my function f of n is big O of g of n, that essentially means that g of n is the upper bound of f of n. So in this case, from the previous example, my f of n could be 2 times n plus n squared, but n squared is my most contributing term, so we will say that n squared actually can be treated as this upper boundary, because if I multiply it by a big enough constant, at some point it will always be above f of n. Okay, so let's try and apply this quickly to the functions that we saw. For 2 of n, what would be the upper bound? Well, all you need to do is figure out which one is the most contributing term. There is only one term here, 2 times n, but actually 2 itself is just a constant, which is not particularly significant. So we will say that f of n equals to 2 of n is asymptotically bound by n. So we will say that in terms of asymptotic complexity, big O of n is the upper boundary of 2n. In this case, 2 can be treated as a constant c in the equation. Just to make this a little bit more visual, so this is the idea. F of n is our actual function that we're trying to evaluate the complexity of. And to simplify, we want to find this most contributing term, be it linear, quadratic, or something else. We want to throw away whatever constant is multiplied by, and we will say that that term makes up the upper boundary of f of n. Great. So what terms can you actually expect to see out there? Well, I guess they vary as much as the functions vary. Here is a quick graph taken directly from the textbook. You can find cubic, quadratic terms, logarithmic terms, linear terms, and even constant terms sometimes in your functions. Which algorithms are more efficient? Well, if you look at this variety of the various slopes, obviously the more shallow the slope is, the better the algorithm. So generally, we want this function to be as the steeper it is, essentially, the less efficient it is. So if I'm given a choice between n cubed and n squared, I would always prefer n squared because it has a slightly shallower slope, therefore it is slightly more efficient. Because obviously we want the time to grow as slowly as possible as n grows. Remember, x-axis stands for data, how fast the data increases, and then y-axis describes how quickly will the speed of your algorithm deteriorate, so to speak, how much more time will it require. And then, of course, the slower this grows, the better. So here is a bunch of examples. Let's quickly try and figure out the big O asymptotic complexity of these functions. For n squared, what would be the most contributed term? What would be the big O of f of n? It would just be n squared, right? So there are no constants to throw away. N squared is the only term, the most contributed term. It is its own upper bound. Second example, we have 1 million times n squared. 1 million is just that constant c that we can throw away. So we will say that 1 million times n squared is basically a quadratic function. Therefore, in terms of the asymptotic complexity, it's just big O n squared. Then the third example is the one of that algorithm C that I showed you before. 2n plus n squared is, once again, we already figured out that n squared contributes the most. It's the heaviest term, so we'll say that this function is also big O of n squared. So as you can see, these three functions are different, but asymptotically, we will treat them as equals. Okay, example number 4, 10 plus n plus log n. So what are we looking at here? 10 is obviously a constant term. So we will say constant complexity. It's not even dependent on n. N is the linear term, right? And then we have log n, logarithmic term. Which one do you think is the heaviest? Well, for that, look at the graph here on the right-hand side. N is clearly steeper than logarithm of n. Therefore, n out of these three terms is the one that contributes the most. So this function f of n, big O of it will be just n. Just a quick note, on the graph you will see that instead of saying log as an log, we simply say lg, and lg is just a shorthand for base 2 logarithm. Why do we want to have a separate notation for base 2 logarithm? Because in computer science everything is binary, obviously, right? We deal with computers, thus it's convenient to work with base 2 logarithms rather than any other logarithms. So we usually express base 2 log as just lg. But this is just your good old log. Great, so because out of the three terms n contributes the most, we will say that the complexity of this function is just O of n. And then final example number 5, we have 10 times n cubed plus 364 times n squared. Again, look at the graph, n cubed is steeper than n squared, therefore that is the heavier term. It would dominate n squared, thus you can throw away n squared, the term doesn't matter. For 10 times n cubed, you can throw away the constant. We only keep the actual term to some power if that is the case, and basically n cubed is the upper bound of all cubic functions. So this essentially tells me that this function is cubic, and that is what matters. Cubic versus quadratic is what matters. Specific constants are irrelevant in the asymptotic context. Great. Okay, one thing we maybe should discuss, what do you think is this line? What does it stand for? If I'm speaking of the complexity of the algorithms, what can possibly have constant complexity? Well, this line actually stands for, like I said, it's constant complexity. In terms of big O notation, we will say it's O of 1, big O of 1. And this essentially means that a given algorithm is not dependent on the data at all. What algorithms can possibly not depend on the number of elements in your array? Well, what if you write an algorithm that, for example, simply reads the input from the user or something like that? It doesn't actually query the data in any way. Or what if your algorithm only has a single statement and that statement simply prints a welcome message or something like that? If your piece of code that you're analyzing does not have any variables set by the user, if no variables can grow or shrink, then you will say, well, you know, this piece of code always have exactly 5 statements. It will always just execute those 5 statements. I do not have any loops. I do not have any structures, essentially, that can grow or shrink. Thus, my piece of code has constant complexity. It's always going to be 5 for this particular piece of code. And obviously, constant complexity is the best complexity because it doesn't get worse as your array increases, but simply because it's not actually linked to the size of the array. I'm using array loosely. Array would be any data structure that you are applying your algorithm to. I know this is maybe a little bit abstract right now, but hopefully you guys are getting the general vibe. The idea is we want to figure out how the size of your data structure relates to amount of time spent processing that data structure, right? And we are trying to express this relationship in a simple mathematical way. We say, let's simplify it. Let's just find the upper boundary of how bad that function is. Is it linear? Is it quadratic? Is it cubic? That kind of general feel. And yes, this is currently what we're doing. We're talking about how to find that simplified expression of the efficiency of an algorithm. Here's a bunch of properties of the big O notation. And again, this might look like a mouthful, but if you look at them individually, they are all actually quite simple. Let's quickly go through them. The very first one says if f of n is asymptotically bound by g of n and g of n is asymptotically bound by some h of n, then f of n is going to be also bound by h of n. So this makes sense, right? if f of n has an upper boundary of g of n, and g of n has its own upper boundary of h of n, then obviously h of n is going to be the upper boundary of both g of n as well as f of n. Property number 2, if f of n is bound above by h of n, and g of n is also bound by the same upper bound, then adding the two functions will not actually change the asymptotic complexity. So if I have n squared and n squared, and then I say, well, what if I have a function which actually does n squared twice, n squared plus n squared? Well, that will give me 2n squared, but that is obviously still a quadratic function, even if I double the n squared. So the sum of my functions that are both bound by the same function will still have that very same function as the upper boundary. Property number 3 essentially tells you that the constants are irrelevant. If you have some term in your polynomial function multiplied by a constant, then we will say that function is basically bound by just the polynomial term minus the constant. So you can always throw away the constant. In the asymptotic context, constants are irrelevant. For the power rule is that you can say that any power is going to be bounded above by a higher power. So like n cubed always kind of beats n squared, n to the power of 4 beats n cubed, etc. They cannot be treated as each other's upper boundaries. But of course, when you evaluate the complexity of an algorithm, you can't take a linear algorithm and say, well, you know, all linear functions are bound by quadratic functions by the power rule. Yes, that is true, but when you evaluate the efficiency of algorithms, you usually want to find the smallest upper boundary. So an upper boundary that is as close to the actual function as possible. All right, 5 is similar to 3. If I have some function which can be expressed as, if I have f of n equal to c times g of n, then you essentially can neglect that constant c. We will say that f of n is bounded above by g of n. For the logs, we will say that any log of base a is bounded above by any log of base b for any two numbers a and b greater than 1. Essentially, we're saying all logs are kind of equally shallow. Base is not really important. We kind of treat the base as another constant in this case. And in fact, for our purpose, rule 7 is very important. We will say that any logarithm is bounded above by the logarithm of base 2. And that is the logarithm we use the most in the computer science context. For obvious reasons, just because we deal with binary log. In case you forgot what a logarithm is, here's a quick reminder. If we have a to the power of y equal x, then essentially a logarithm given a and x allows you to calculate that power to which you need to take a to get x. So log of base a of x will give you y, right? Y is the power to which we're taking a to get x. Great, and here is just the picture of some logarithms. As you can see, the smaller the base, the steeper the log becomes. So it's only natural that we treat log base 2 as the upper bounds to all the other logarithm functions. Okay, so that was Big O in a nutshell. Hopefully it is making a little bit of sense to you. I strongly advise that you also read the textbook on this. The textbook is quite detailed on the mathematical aspects of what we're talking about, so it might be good to refer back to the textbook to supplement what I am showing you in the slides. But hopefully you are getting the gist of it. Okay, so given a function, we now know how to extract the complexity of that function. Just find the largest term, discard all of its constants, discard all of the other terms, and that is your Big O expression. But the question is, given a piece of code, how do we actually convert it to a function? How do we figure out what that function is? Well, generally, in terms of the algorithms, how do you, what contributes to the complexity of an algorithm? Obviously, the more operations an algorithm takes, the longer it will execute, right? If one algorithm has only 2 lines of code and another algorithm has 3 lines of code, then 3 lines is longer than 2. So generally, every single operation of an algorithm will be treated as a data item, so to speak. So when you're looking at a piece of code, and you want to figure out its efficiency. What you want to find out is how many operations will an algorithm perform. What operations actually happen behind the scenes when you execute a piece of code? Every single time you create a variable, that is an operation. You have to go to computer memory and actually allocate some space in memory to store data. Every single time you assign data to a variable, that is also an operation, because once again, you access the reserved memory and you store data in it. Every single time you read a variable, that is also an operation. Every single time you compare two variables, that's an operation. Every single time you do some math, you add the data, you add some value to your variable, you subtract some value from your variable, you multiply, you divide, etc. Every single mathematical operation is also contributing to the overall complexity. So if you want to be extremely pedantic, the correct way would be to go through your algorithm and to calculate the exact number of operations taken by your algorithm. However, just because we work with variables a lot, it turns out that sometimes you can simplify things a little bit by only considering the assignments. In other words, let's, for simplicity's sake, not, for example, count mathematical operations. Let's assume that only reading or writing, in this case, writing data to memory is what really takes time while we execute our algorithm. So out of all of the operations, let's only count the assignments. Okay. So here is the very first example. We have a very simple piece of code here. We have two variables I and j. Both of them are set to some values. I is set to 0, j is set to 1. So that's immediately two assignments right there. And then we have a while loop. As you can see, I'm not working with arrays. Like I said, I have used the term array, size of the array, previously in a loose kind of manner. What we do have here is some unknown variable n. We do not know how large this n is. It can be 1, it can be 100, it can be 1 million. We do not know how many iterations this while loop is actually going to take. But we do know that we will have to go all the way from I equal to 0 all the way to n. So whatever happens inside of the while loop will obviously execute n times. I'm sure you agree, from 0 to n. What happens inside of the while loop? Well, we're going to increment I, and obviously an increment is an assignment, because you take I, you add 1 to it, you assign that value back to I. We also add 2 to j, so once again that is an assignment. We take j, we add 2 to it, we write that value back into j. So we have two assignments here and two assignments inside of the while loop. So if we only count the assignments as operations that contribute to the complexity of our code, the question is, how many assignments in total will this code execute? Well, like I said, this is 2 and this is 2, but what is very important, these two assignments right here are nested inside of the while loop. And that while loop will execute an unknown number of times. It will execute n times. So if I was to express this as a mathematical formula, I will say, well, the total number of assignments is 2 plus 2n, right? N here stands for this counter of the while loop. We do not know how many times, but definitely n times, no matter how big or small n is. And every single time the while loop executes, two assignment operations are going to happen, and that's what the second 2 stands for. All right, great. So we got our first formula out of a piece of code. Total number of operations based on just the assignments performed. What is the complexity of this algorithm? We already know how to deal with this. We have two terms, a constant term and a linear term. We need to find the one which is heavier. Obviously, linear is steeper than totally flat, constant. So between 2 and 2n, we're going to favor 2n as the more likely to be the upper bound. And now because 2n also has a constant, n is multiplied by 2, we're going to throw away that constant. So the only thing that we're going to be left with is n. We will say that the complexity, asymptotic complexity of this particular piece of code is O of n. In other words, it's linear. I'm sure you agree. As n grows, the amount of operations will grow linearly. If n is equal to 100, I will need to perform these two assignments 100 times. If n is equal to 1,000, I will need to perform these two assignments 1,000 times, etc. So Yes, the larger n is, the longer I will take to execute all the assignments, but time grows, compared to the data, time grows at a nice linear fashion. Okay, let's go further. So for the rest of the lecture, I just want to show you essentially how to figure out what the big O complexity is given a piece of code. And this is exactly the kind of stuff we will ask in the tests, TAT tests, examination opportunities. So out of this entire lecture, the main takeaway is, if I throw a code snippet at you, will you be able to count the assignment and then figure out which term contributed the most? Great, so let's do this example then. How many assignments in total? If you do count the mathematical operations, you will end up usually, and the comparisons are also operations, you will usually end up with the very same solution. That is why we say just counting the assignments kind of simplifies your life a little. All right, so how many assignments? This is definitely one assignment. This is one assignment, this is one assignment, right? The increments are the assignments, but the tricky part here is we have two for loops that we need to take into account. And this is actually the formula to help you figure it out. I have color-coded it for you, so let's quickly go through it to make sure we can map all the numbers to all of the assignments. Okay, so this assignment happens only once. My k equal to 0, that's my very first assignment. Then I enter my first for loop. This for loop is going to execute n times, from 0 to n, right? What happens inside of this for loop? Well, only once, in the very beginning, I will initialize this counter I. So this is where my second one comes from. And it's not inside of any loop, it's not multiplied by an n, because you only need to initialize this counter once. Then I know this for loop will execute n times, right? So that's where this green n comes from. What is going to happen inside of the for loop? Well, every single time the for loop goes into the next iteration, it's going to keep incrementing its counter I. So that's one assignment inside of my parentheses. Additionally, for every single iteration of this for loop, we will execute a whole other for loop inside of it. For this for loop, what is going to happen? Well, we will initialize j, and we will do this n times because this for loop will be run n times by the outer for loop. So that's where this blue one is from. It's for initializing j. Then finally, this for loop itself will also run n times from 0 to n. So that's where the second n is from. And then inside of this for loop, we will increment j for every single iteration, and also we will increment k. So that's where my two gray ones come from. Okay, we have counted all of the assignments. We can now add all of these values together, open the brackets, and you will see that the final formula that you get is 2 plus 2n plus 2n squared, right? Those are my n's. Okay, what is the complexity of the algorithm? Once again, find the heaviest term. You already know that between constant, linear, and quadratic is the biggest deal. So clearly these two can just be thrown away. And for 2n squared, 2 can be neglected as a constant. So n squared is the only thing that really remains. So the complexity of this piece of code is n squared. Also want to help you visualize this so that it doesn't become this, black magic that you just memorize for the test. Big O complexity is actually a very simple and natural way of kind of guesstimating how long your piece of code will take. So when I have a nested for loop, what exactly happens? Our outer for loop will execute, some n times. And then I think, all right, and every single time I go into an iteration of the for loop, I have another for loop nested inside of it. So for that nested for loop, every single time it executes, it will give me another, n times, and another n operations. And this is how I get n squared. As you can see, this is a perfect square right here. I will have n for the outer loop, I will have n for the inner loop. And of course, if my n is large enough, this square will become quite large, right? So nested for loops generally always give you quadratic complexity, specifically because you have some n multiplied by some m. These two values do not necessarily have to be the same. I can have two different counters. And then if I have an n and an m, for example, the complexity would not be n squared. It would rather be big O of n times m, for example, if you have two variables in the equation. which will still typically, well, not typically, but technically be quadratic. All right, let's do another example. Here is another nested for loop, and this one is slightly different. We start from I of 0, we go up to n. So the outer one you've already seen before. You know this will execute n times, so complexity is at least linear. Now we have a nested for loop, so you expect the complexity to be quadratic. But is it really going to be the case? Let's look at it. We have two counters for the second for loop, j equal to 0 and some sum equal to 0, just an initialized variable. Then what's very important is this comparison right here. We will iterate while j is less or equal to I. But what's important is I starts at 0, j also starts at 0. So the first time you enter this for loop, I is 0, right? I is very, very small. J is also equal to 0, so j is equal to I, but the first time around, this second loop won't execute n times, it will only execute once, right? Because to go from 0 to 0, you just do a single step and you already are there. Second time around, when my first for loop increments the I becomes 1, j will again be initialized to 0. So to go from 0 to 1, we'll actually take two steps. I will do one iteration for j equal to 0, one iteration for j equal to 1, and then I'll be done with it. Next time around, I again is going to increase a little bit more. So instead of 2 steps, we'll do 3 steps, then we'll do 4 steps, then we'll do 5 steps, until eventually I reaches n, and only on that last iteration of the outer loop will my inner loop also go for n iterations. So how do we actually express this mathematically, and what complexity is this going to give us at the end of the day? Like I've said, we will have a bit of a progression for the second loop, right? So if I was to kind of make it a little bit more relatable here, so 1 stands once again for initializing I, 3n would be just these 3 initializations, incrementing I. Yes, it will happen n times, we know that. Assigning j to 0, setting 0 to sum, those are my kind of 3 initializations, right? That's why the 3n is there. And then what we have here is 2 stands for these 2 assignments right here, but what matters is we don't just multiply 2 by n, we rather go from 1 to 2 all the way up to n. So how do you actually measure the complexity of this? Well, it helps to know a certain formula, which you might have seen maybe in linear algebra, if you have done linear algebra here at the varsity. A sum of values from 1 all the way up to n can actually be expressed by n times n plus 1 divided by 2. This formula was derived by a German mathematician surnamed as Gauss. I think the legend goes that in school he was given a task of adding all the values from 1 up to n, but he was too lazy to actually do it by hand, to go all the way from 1 to 100, so he figured out a nice quick formula to give him the solution. But what matters is this part here, we can actually replace by this formula right there, which gives us, not very surprisingly, a quadratic term. I'm sure you can see that if we open these brackets, we will have n times n plus n, right? So what is then the complexity of this algorithm? It is obviously quadratic. So again, a nested loop gives us a quadratic complexity, even though the second loop only starts with a single iteration and then 2 iterations and then 3, etc. But again, if you try to visualize it visually, you will see why quadratic complexity still applies. So yes, outer loop has n iterations, that's just a given. Now what happens for the inner loop? We start with just 1 iteration, then we go to 2, then we go to 3, then we go to 4, etc., etc., until eventually we reach n iterations for the very, very last iteration of the outer loop. So when the outer loop has reached its final iteration, then the inner loop will also do n steps. So what you're looking at pictorially is only half of the square. You get this triangle. But half of the square is essentially n squared times 1/2, right? And remember, constants are irrelevant in terms of asymptotic complexity. So even though we're not looking at the full square, we're looking at half of the square, the square part is still there. We still have n squared as one of the polynomial terms. Therefore, the complexity is still quadratic, even though this will run slightly faster exactly 1/2, it will take half as much time as the algorithm on the previous slides. But still, if you compare this piece of code to a piece of code which doesn't have a nested for loop, this piece of code, a nested for loop, will still be slower than a piece of code without a nested for loop. All right, another example, nested for loop. Should we just skip the calculation and assume that the complexity is n squared? Well, it turns out that's a bad idea, because not every for loop is the same, right? You always need to look at the conditions of the for loops. In this case, my second nested for loop goes from 0 to n, but the first one actually goes from 0 to 10 rather than to n. So even though my second for loop depends on some unknown variable n that can potentially become very, very, very large and thus really slow down my algorithm, I know that the outer loop will always execute exactly 10 times. So my outer loop doesn't add n to the equation. Instead, it adds a constant. If you open all the brackets, you will, your formula is going to be 21 plus 20n. And if you look at this formula, you will see that the quadratic term is actually not present. This algorithm is in fact linear rather than quadratic, and the reason for it is only the second for loop is dependent on a variable that can become smaller or larger, and the first one is essentially a constant. It always executes exactly 10 times. Even if your n becomes 1 million, the outer loop will still execute 10 times, and yes, overall it makes your code 10 times slower, but it's not a term, it doesn't change the polynomial formulation of the complexity of your algorithm. So watch out for this also in the tests, because we will try to catch you out on this, right? Don't just assume that the nested for loop is always n squared. It really depends on whether you know all the counters, whether some of them are constant or not. Here's another tricky example. We have 4 nested for loops. So should we just assume it's n to the power of 4, right? Every single time you add a for loop, you obviously slap an n onto that equation. Well, again, things are not always what they seem. You have to always apply your mind before you just assume the answer. So let's quickly break this down. So we already know the outer loop is going to give us an n, inner loop is going to give us another n. Then this for loop is going to give us another n, but what is going to happen in the very, very last one? Let's look at the counters. We set m to I minus 2, and then m is going to go up to I. So the question is, if this loop executes n times, if this loop executes n times, if this loop executes n times, it's just n, 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 so far we definitely have arrived at least at n cubed, what would be the number of iterations for the very, very last loop? How many times will the innermost loop execute? I usually pause here. If we were in class, I would maybe ask you for some ideas, but if you look at it, this is a bit of a trick question. It looks like you use a variable I, but actually if we go from I minus 2 to I, does it really matter what I is? If I is 0, our m is going to start at minus 1, and then it will go up to 0. So how many steps will it take? Minus 2, minus 1, and then we'll reach 0. 3 steps. If I was equal to 2, how many times will this execute? 2 minus 2 gives you a 0. We want to go from 0 up to 2. 0, 1, 2. Once again, 3 steps. So it's almost like it doesn't matter what I is. The inner loop would always execute exactly 3 times. Well, minus or equal if this was less or equal. If this was just less, it would be 2 times. But mathematically, you can even take your final condition and subtract to it the starting condition. I minus 2 would actually give you a 2. So it's definitely a constant number of iterations that your inner loop is going to execute. Therefore, it's not going to contribute to the power of n in your final expression. Thus, the complexity of this piece of code is actually cubic, not n to the power of 4. Let's again shake things up a little. Here is a for loop wrapped inside of the while loop. Is this going to be different? Well, let's again look at the conditions. Here we go from I to n. I is set to 9. We go from 9 to n, not from 0 to n. So that's going to be n minus 9, right? But still n is clearly in the equation. What about this for loop? Oh, actually, look at this. It's the same trick. We go from I minus 8 all the way up to I, so it will execute exactly, well, 9 times in this case, right? So even the while loop is dependent on n, because the second loop is not actually dependent on n, the complexity is going to be linear. How about some recursion? Can we apply the same ideas to recursive functions? We most definitely can. Again, think, in this case, you are not looking at the loop, but remember, recursive functions can easily be, quite often can be translated to iterative functions. So what I have here is a recursive function that starts on some n, and then it keeps recursing, keeps calling itself until it reaches an n of 0, right? So we go from n to 0. And every single time, we're going to subtract 1 from that n until we reach 0. So clearly, we go from n all the way to 0. Every single time we chop just one piece away from it. What do you think is the complexity? Well, this piece of code can be rewritten as just a simple for loop that goes from n to 0. Single for loop without any nests in it, without any nested iterations. So complexity is actually just going to be linear. So recursion is not always scary, although sometimes it can be. Here is a recursive formula for generating Fibonacci numbers. I think this is an example that we have covered in course 110 last semester. So you start on some n, and then again you go from n all the way down to 1. And for every single call of the recursive function, you are going to return to a summation of Fibonacci n minus 1 plus Fibonacci n minus 2. So what do you think is the complexity of this function? Is it going to be big O of 1 plus O n minus 1 plus O n minus 2? Can we somehow break it down like that? Well, not exactly. You always need to think, all right, as my n grows, how many more function calls will I actually encounter, will I actually execute? And if you draw this out, you will see that the number of function calls doubles every single time you increment your n. So if n is 1, you only do a single function call. For 1, you immediately reach a stopping condition. If your n is 2, then you already have to double the number of function calls. You will call f on 0 as well as on 1 here. If you increment n again, if you go from 2 to 3, then you will double it once again. From 3, we're going to split into 2 function calls, for 1 and for 2, and then 2 also will split it into 2 calls. So every single time we only increment your n, the amount of time actually doubles. So we keep multiplying by 2 every single time our n is incrementing. What do you think how can this complexity be expressed? Well, clearly, if we keep multiplying by 2, we are looking at powers of 2. That kind of a complexity is known as exponential. So the big O of this particular piece of code is O of 2 to the power of n. Just because I have this branching tree, it means that I will actually quickly have lots and lots and lots of function calls, even if my n is quite small. So do you think exponential complexity is good or bad? Is it high complexity or low complexity? Is it a slow algorithm or a fast algorithm? It's actually very slow. In fact, as slow as it gets. Exponential complexity is basically the worst thing you can encounter. Sometimes it's unavoidable, but generally speaking, the exponential curve is the steepest of them all. So if you can help it, try if you ever given a choice between exponential complexity and, let's say, cubic complexity, even though cubic might sound bad, it will still not be as bad as exponential. And here is the final example. What if we have some kind of a non-linear step in your for loop rather than just incrementing or decrementing? Let's look at this particular simple example. So we have a for loop. We start at some n. We want to go from n to I, but what's very important, we won't actually be decrementing I. We will rather be dividing I by some factor every single time. How do we figure out how many times will this for loop execute? Well, we obviously start at n, and then immediately after a single iteration has happened, we are going to go ahead and halve our n, right? So we start with I equal to n, Second time around, we're going to take 1/2 of n and see if 1/2 is greater or equal to 1. After you have done your second iteration, you're going to halve the half of n, and once again see if that quarter of n is still greater or equal to 1. If it is, you're going to do another execution, then you're going to halve the quarter, you're going to get 1/8 of n, you're going to compare 1/8 of n to 1. If it's still bigger than 1, you're going to keep going until eventually you find, you divide the n by 2 so many times that it becomes smaller than 1. So these are the values, if we were to express them with powers of 2, these are the values that I is going to take. So at first, 2 to the power of 0 is obviously 1, I takes the power of n, then it's going to be half of n, etc., etc., until eventually we divide it so many times by 2 that I becomes smaller than 1. So what we want to know is, what is that power of 2, right? How many times can we actually divide n by 2 until we reach 1, until we reach that breaking point? And to figure out what m is, let's say, okay, so we're going to stop when n divided by 2 to the power of m is 1. So m is the number of times I can divide my n. How do I figure out what m is? Well, we already recapped logarithms previously. Logarithms are these amazing functions that allow you to figure out what the power is. What power should be given some a to the power of x equal y, what that x is. Simply take a log of a necessary base, in this case base of 2. So let's rewrite this expression as 2m equals n. And now to figure out m, simply calculate base to a logarithm of n. So what this boils down to is, if I ask you again how many times does the loop execute, you can safely tell me that it will execute base to log of n times. Therefore, the complexity of this algorithm is base to log of n. And remember, I told you the base to logs are simply written down as lg. Skip the O just to make the notation smaller. All right, so logarithm complexity is achievable. Remember, if you remember all of the curves, logarithm was actually quite shallow. Logarithmic complexity is very good. This is clearly a very fast algorithm. Why is this for loop faster than a linear for loop where you just decrement I? Well, because if you halve your n every single time, you will obviously go through the search space a lot faster. Let's say if you have 100 items. If I was decrementing, I will have to go from 100 to 99, 98, 97, 96, etc. until I reach 0. If I go with halving it every single time, from 100, I jump straight to 50. From 50, I jump to 25. So I start with very large steps through the search space and I quickly narrow it down to the end, so I do not look at every single item in my array, for example. You have seen examples of algorithms that have logarithmic complexity. And again, if we were in class, I'd ask you what they are. But if any of you remember binary search is a great example of a logarithmic algorithm, because it takes your sorted array, it goes straight to the middle of the array, and then it chooses which half to search, the left or the right. And once the side has been chosen, the other side will be neglected. So that kind of search is obviously a lot faster than looking at every single item in your array. So basically, what kind of algorithms exhibit logarithmic complexity? It's those that divide up the search space non-linearly. All right, this is the last slide that I have for you guys today. I hope this made sense. If it didn't, please ask me questions on Discord in the lectures channel. You can also write me an email, speak to our tutors, and please do open the textbook. Make sure you are comfortable with the concept of logarithmic complexity, because this is going to be examined. And also we will refer to this material a lot for the rest of the semester. So please make sure you are on board with this. Great, thanks a lot. In the next lecture, we will discuss skip lists, the first data structure of course 212. Thanks a lot for your attention.